In this video, we continue to learn about Raoult's law by examining deviations from that law. Okay, Raoult's law allows you to establish a relationship between the vapor pressure on top of a liquid and the concentration of the components in that liquid mixture. So what we're really examining here is as follows, right? So you have here a mixture of liquids A and B, and you have here some vapor pressures of A and B from the molecules that are at equilibrium with those liquids. And the question that you're simply asking is how does the vapor pressure of A changes when the concentration of A in the liquid changes, and the same thing for B. Alright, so we have seen that under ideal solution circumstances, the law that actually allows you to do that is Raoult's law, where you find a linear dependence between the vapor pressure in the gas phase and the concentration, the mole fraction, in the liquid phase. Right, and what that means is that if you do vapor pressure versus composition diagram in the liquid, right, you're going to get here some straight lines connecting the points from no presence of this liquid A to pure liquid A, and that will be the vapor pressure of A when pure. And then the other component is going to have something different, okay, which will be, in this case, this is going to be x sub b going from 0 to 1. Okay, great. Alright, so then the idea here, this will be the vapor pressure of B when pure. Okay, so this happens for ideal solutions, and again we have defined ideal solutions as those in which the components A and B are similar in nature, such that the interactions of A with B are of the same type of the interactions of A and B with B. So for example, benzene and toluene, very similar molecules, and you can see how the way that toluene will interact with benzene is going to be similar to the way that benzene interacts with benzene and toluene interacts with toluene. Okay, great. But of course, that's not always true, right? You not always have ideal solutions. For example, if you were to mix, say, benzene with water, you would be hard-pressed to find that Raoult's law applies throughout the concentration range. And actually, that's the case for most solutions. They do not behave ideally. So what we're going to do in this video is quickly examine a couple of limiting cases for deviations from Raoult's law. The first one is one in which you have something that is called a positive deviation. Right, so let me see if I can add here a few more lines. Remember that this is the total pressure. Right, so this is simply the sum of the black and red lines, that is just the blue line, the total pressure on the mixture, on top of the mixture. So that will be the vapor pressure of A and B at any concentration. Now, this is going to be a positive deviation that I'm going to write here. And in a positive deviation, what happens is that the vapor pressures that you measure are actually larger than those produced by Raoult's law. Right, so if we take the line of B, right, which goes from 0 to 1, then the vapor pressures that happen in reality are actually a little bit above Raoult's law prediction, right? So that would be what happens in reality if you have a positive deviation. Then for component A, you're going to have exactly the same thing. Let me actually see if I can get the right marker, right? So it's going to be a little bit above the prediction of Raoult's law, and for the total, you're going to have exactly the same, right? So for the total, it's going to be something like this. Okay, so for example, an instance of this type of positive deviation will be a solution formed by carbon disulfide, which is this liquid, and acetone or propanone, which is CH3, CO, CH3. Notice that this molecule does not have a dipole moment, it's apolar, and that molecule has a dipole moment. Right, so the way that they're going to interact with each other is not the same as carbon disulfide interacts with carbon disulfide and propanone with propanone. Right, so what this actually is telling you is that those molecules, that interaction is not favorable, right? Because what you're seeing is an increased tendency for the molecules in the liquid phase to escape into the gas phase, right? The vapor pressure is larger than predicted by Raoult's law. And again, that means that the repulsions, that the interactions are favorable, right? So the molecules of carbon disulfide and acetone repel each other more than they do among the pure liquids. And that's why you have that increased vapor pressure in the gas phase, right? So that is a positive deviation. And of course, you guys can anticipate what's going to happen for a negative deviation, which will be exactly the opposite. So let's redraw here a few. First, we're going to start with Raoult's law predictions, which I'm going to draw like this for component A, and then I'm going to draw like this for component B. All right. X would be 0 and 1. Okay, starts from 0 and goes all the way to 1. So that will be Raoult's law, and then the overall pressure on top of the mixture will be right here. Let me write here what the vapor pressures are when pure. That will be P of B star, the vapor pressure of liquid B when pure, and this is going to be the vapor pressure of A when pure. Alright, so for a negative deviation, what you will find is that the vapor pressure that you measure is below the expectation from Raoult's law. So Raoult's law is the straight line, okay, that law, but then in reality what you observe is that the lines are actually below Raoult's law. That will be for component A, and then for component B you're going to have also a line that is below Raoult's law for component B, and for the total you will have exactly the same thing. Right, so that's going to be more or less how this looks like. So there is a negative deviation, and then we can use this knowledge to learn a little bit about the interactions of those liquids in solution. So what happens here is that if there's a decreased tendency to put molecules into the gas phase, that's because those molecules in the liquid phase are stabilized much more so than in an ideal solution, right? So what that means is that A attracts B more strongly than A attracts A or B attracts B. Okay, and these solutions also exist. For example, the solution formed by chloroform, CHCl3, and acetone, CH3COCH3, are such that chloroform attracts acetone much more tightly than it does chloroform itself or acetone with acetone, right? So that will be a negative deviation as well. All right, so, in this particular case, then, the question is, well, notice that our work with the chemical potentials is based on the fact that this has to be an ideal solution, right? Raoult's law needs to apply. But of course, when you have these sort of deviations, then Raoult's law does not apply, or at least it does not apply throughout. So the question is, well, what can we do? Well, in the next videos, we're going to try to learn what happens when you don't have ideal solutions and how you can begin to think about writing the chemical potentials for, again, liquid mixtures that are not ideal.